Hello guys, and welcome once more to this new video on my YouTube channel. So today we are simply going to continue solving Cameroon DC examination, pure mathematics mechanics paper 3, June 2022, question 6 actually. So the question was divided into two parts, that's question 6 Romans 1 and question 6 Romans 2 actually. Question 6 Romans 1 reads: forces F1 equals negative I plus 2J plus K Newton and F2 equals 3I plus 6K Newton act through the point with position vectors R1 equals I minus J plus 3K meters and R2 equals negative 3I plus J minus 3K meters respectively. Show that the lines of action of these forces intersect and find the position vector of their points of intersection. Question 6 Romans 2 reads: the acceleration of a particle starting from rest is 10 divided by v meters per second squared, where v is the speed of the particle at time t seconds. Find the speed of the particle when t equals 5 seconds. Let us then actually move into the solution of this question. That is, we are going to start by solving question 6 Romans 1 actually. So we are given a force F1 which is equals to negative I plus 2J plus K Newton, and this force F1 acts through a point having position vector R1 which is equals to I minus J plus 3K meters actually. We also have a force F2 which acts through a point with position vector R2 equals negative 3I plus J minus 2K meters actually. So in the first part of the question, that is the first part of question 6 Romans 1 actually, is asking us to show that the lines of action of each forces intersect actually. To do that, in the first place, we have first of all to write the vector forms of the line of action of each forces actually. Yes, let us start by writing first of all the vector form of the line of action of the force F1 actually. Writing that, we are simply going to have the position vector of the point through which the force F1 acts, that is I minus J plus 3K, which is actually R1, and then the force F1 actually. Doing the same thing, that is writing the vector form of the line of action of the force F2. Let that be equals to L2 actually. We are going to have negative 3I plus J then minus 2K, which is actually the position vector of the point through which this force F2 which is 3I plus 6K acts actually. Yes, so since we already have these two vector forms of the line of action of each forces, we have to put the assumption, that is, let us assume that the two lines intersect actually. Yes, so let us assume that the two lines intersect. If the two lines intersect, it simply implies that L1 is going to be equals to L2 actually. Writing that, it implies we are going to equate these two corresponding. We are going to equate this, that is L1 and L2 actually. So equating the term, then we are going to have I minus J plus 3K then plus gamma times negative I plus 2J plus K is equals to L2 which is L2 is equals to L2 is negative 3I plus J minus 2K plus mu times 3I plus 6K. Expanding the left hand side and the right hand side, we are going to obtain the left hand side to be I minus J plus 3K. Then gamma times negative I gives us negative I gamma. Gamma times 2J gives us 2J gamma. Then gamma times K gives us gamma K actually. This equals to negative 3I plus J minus 2K then plus mu times 3I gives us 3 mu I, then mu times 6K gives us 6 mu K actually. Yes, bringing like terms together on the left hand side and right hand side, we are going to obtain on the left hand side that if we bring like terms together, that is the I and the I all together, we are going to obtain 1 minus gamma then times 1 minus gamma in bracket then I plus open bracket negative 1 plus 2 gamma J plus 3 plus gamma K on the left hand side actually. Doing same, that is bringing like terms together on the right hand side, we are going to obtain negative 3 plus 3 mu I, then plus J plus open bracket negative 2 plus 6 mu then K actually. Yes, So what are we going to do here? Simply, we are simply going to equate actually coefficients. That is the coefficient of I, okay, in the coefficient of I actually on the left hand side, okay, is going to be equal to the coefficient of I actually on the right hand side actually, and we do same for the j and k components actually. Doing that, actually we are going to obtain that 1 minus I, that is the coefficient of I on the left hand side, which is 1 minus gamma, excuse me, which is equals actually the coefficient of I on the right hand side actually, which is equals to negative 3 plus 3 mu actually. Let us take this to be our equation 1 actually. Doing same for the j and k component, what are we going to obtain? For the j component, we are going to have negative 1 plus 2 gamma to be equals to 1 actually, because 1 is a coefficient of j on the right hand side actually. Let us call this our equation 2, and we do finally for the k component, that is 3 plus gamma, which is the coefficient of k on the left hand side, which is equals to negative 2 plus 6 mu, which is the coefficient actually of k on the right hand side actually. Let us call this actually our equation 3 actually. So in order for us to show that actually the line of action, okay, of the two forces intersect, we simply need in the first place to determine the value of mu and gamma, and then substitute those values of mu and gamma. For example, if you find the value of mu and gamma, okay, in this situation, in this systems of equation, once we are going to obtain the value of mu and gamma, we can substitute the value of mu and gamma, okay, into equation 1 and equation 3. If, okay, the right hand side is equal to the left hand side, therefore we conclude that actually the line of action of these forces actually intersect. Or we simply come and substitute the value of gamma in equation 2. And if the left hand side actually is equal to the right hand side, which is 1, therefore we can also conclude that the lines of action of these forces actually intersect actually. Yes, let us now determine the value of lambda, the value of gamma and mu actually. Yes, so doing that is from equation 2, we can clearly see that gamma is equal to actually 1, okay, from equation 2, from which we can therefore substitute the value of gamma into equation 1 actually. So substituting the value of gamma into equation 1, since we know that gamma is equal to 1, we are going to have actually that 1 minus gamma which is 1, to be equal to negative 3 plus 3 times mu actually, mu which therefore going to be equals to 1 actually. That is, we are going to have 0. Then if you send it on the other side, we are going to have 3, which is equals to 3 mu. Then dividing all through by 3, we are going to obtain the value of mu to be 1 actually. Yes, since we already have the value of mu and the value of gamma and mu, we can then go and substitute them into any of our equation 1, either equation 1 or equation 3, substitute them, or we simply come and substitute the value of gamma into equation 2. If the left hand side is equal to the right hand side, we therefore conclude that the lines of action of these two forces actually intersect. Yes, so in this case we are going to substitute the value of gamma and mu into equation 3. Doing that, we are going to obtain 3 plus gamma, which is 1, to be equals to negative 2 plus 6 times 1, which is the value of mu actually. Further simplifying, we are going to obtain 4, okay, 4 on the left hand side and then 4 on the right hand side actually, from which we can therefore conclude that hence the line of action of these two forces actually intersect. So you could also take the value of lambda of gamma, as I said, the value of gamma and mu, okay, substitute it into equation 1, as we're going to get the same result. Or you simply take the value of gamma and substitute it into equation 2. If the left hand side equals to 1, we therefore conclude that the line of action of these two forces intersect, for which we have already proved, because we saw that 4 actually is equal to 4, which actually comes out with our brief conclusion that is the line of action of these two forces actually intersect. Yes. Now let us now get to the next part of the question. That's the next part of question 6 Romans 1, which is asking us to get the position vector of their point of intersection actually. To do that, we are simply going to substitute either that two way. You can either substitute the value of gamma, okay, in L1, okay, or you substitute the value of mu in L2 actually. Let us substitute the value of mu actually into line 2, that is into L2 actually. Then we are going to obtain L2 to be equal to negative 3i, okay, then plus j minus 2k plus 1, which is the value of mu actually, times 3i plus 6k actually. We therefore get the value of x2 to be j plus 4k actually, which is actually the position vector of their point of intersection. You could also take the value of gamma, okay, gamma which is 1, and substitute into L1. You are still going to obtain the same result. Let us try and see whether it gives the same result. If we substitute the value of gamma here, gamma which is 1, we are going to have then I, okay, taking the I components together, we are going to get I. Since gamma is 1, you are going to get I minus R, which is for 0. Taking the J component, that we are going to obtain negative J, then plus gamma, which is 1, then plus 2. 1 times 2J gives us 2J, then you are going to have negative 1, then plus 2J, this is of J, of course. And then the K component, we are going to have 3, then 3 plus gamma, which is 1, then 3, okay, 3K, okay, yes, 3K, then plus K, which will give actually 4K. You have clearly seen that even if you substitute the value of gamma into L1, you are still going to obtain the same result. When we therefore conclude that actually J plus 4K is actually the position vector of their point of intersection actually, which answers finally the question, the first part of the question, that is question 6 Romans 1 actually. Let us now move into question 6 Romans 2 actually. Question 6 Romans 2, we are given an acceleration A which is equals to 10 divided by v meters per second squared actually, and where v is the speed of the particle at time t seconds actually. We are being asked to determine the speed v when the time t equals 5 seconds. To do this, actually, we know that acceleration, okay, in terms of velocity is simply the derivative of velocity with respect to time. That is, acceleration is equals to dv dt actually. Yes. So we can, okay, bring the items together. We can simply put in the value of a actually. We know that a actually is equals to 10 divided by v actually. So a is equal to 10 divided by v, which is equals to actually dv dt properly. Yes. But we can simply, okay, we can simply cross multiply. That we are going to have dt times 10, then dv times dv actually. Yes, this is for us to bring the terms which are corresponding to each other for us to launch the integral properly. Yes, so we can therefore integrate both sides actually. Integrating both sides, that we are going to put the constant outside. We are going to have 10 times the integral of t, which is equals to the integral of v dv actually. Yes, integrating this, we are going to obtain v squared divided by 2 to be equals to 10 times t, then plus k, that is the constant of integration actually. But we know that at rest, okay, the value of v equals 0 and the value of v equals 0 and the value of t equals 0, for which you can therefore get the constant k equals 0. In fact, what am I trying to do actually? Here I'm first of all trying to obtain the constant, okay, which I already obtained, which is 0. Once I have the constant, I can then substitute the constant here and get the value of v, for which t is equals to 5 seconds actually. So that's what I'm trying to do actually. Or you could simply put the bounds. You could also put the boundaries of integration actually. Yes. So if you were the one, okay, that you wanted to put the boundaries actually, here you have included 0 to t, okay, then 0 to 5, then here you have included 0 to v actually, from which you are going to get v from here, okay. Or you can pass through this method, that is getting the constant of integration k, okay, from which I will then come and substitute it in here into this equation and then find the value of v, for which the time t equals 5 seconds. Yes, so then that I'm going to obtain actually, so the speed of the particle when t equals 5 is going to be what? V squared divided by 2 to be equals to 10 times 5, then plus k which is 0, so I didn't include actually the k there, so k which is 0 actually. Yes, so doing this, we are going to obtain, for simplifying further, we are going to obtain v squared to be equals to actually this, we are going to obtain v actually to be equals to 10 meters per second actually, which is actually the speed of the particle when t equals 5 seconds actually, which was actually what was required for us to do actually in the equation. So thank you very much for watching this video. Don't forget to like, okay, to share, to subscribe and comment actually for the YouTube channel to grow actually. So thank you very much for watching this video, and see you then for a very next interesting video concerning mechanics. Thank you.